The new 2018 code provides both a challenge and an opportunity. The challenge is learning more about building science and building performance. The opportunity is when we get these details right, we can better manage risk and liability. I'm Peter Yost of Building Right, and today I will show you real-world examples and specifics in how the new code draws relationships between moisture management, air sealing, and insulation. I will talk about other ways to assess air leakage, some specialized air sealing materials, and of course, that sticky stuff. When air leaks into or out of a building, there is a double penalty: the energy inefficiency of conditioned air being lost, as well as the moisture moving with that leaking air. If that leaking air hits a cold surface inside our walls or roof, the resulting water is likely hidden, creating problems we can't even see. And air leakage is really sneaky. It takes true attention to detail to beat it. The code has a new focus on air tightness. We have new materials and tools to better manage air leakage as well. We have new materials such as liquid flashing. Infrared cameras reveal patterns of heat loss, such as in this image of a timber frame cathedral ceiling. The streaking or blurring is not a poorly focused image, but reveals the air leakage in the roof assembly. And perhaps most importantly for air leakage, the blower door measures the air tightness of a home, a test that the new code now requires. When we air seal a building, we need to connect a whole bunch of different materials together to get continuity. You can see that this idea of continuity is built right into the code, starting with the definition of air barrier. Remember, we are using the terms barrier and control layers interchangeably. We are going to need real focus to connect all the materials to get the building airtight. This image is conceptual and does not show the details of each layer, but it represents how we need to think of control layers as continuous and prioritized, with air being number 2. The building code does not actually define what air impermeable means, except in its definition of air impermeable insulation. Air impermeable insulation is defined as having air permeance less than or equal to 1/50th of a liter of air getting through 1 square meter of material in 1 second at a pressure of 75 pascals, which is about the same as a 35 mile per hour wind. Well, that's a complicated expression, but it means air tightness is pretty tight. But it really means that you can't start your air control layer with a field material that does not meet this ASTM standard, as determined by a third-party independent certified lab. All the materials on the left qualify as air impermeable, starting with drywall, the actual material they chose as the threshold material. Most building professionals are surprised to see that cellulose insulation is not considered air impermeable. It does not mean that cellulose is not significantly more airtight than fiberglass. Cellulose is many more times airtight than fiberglass insulation. It's just that cellulose by itself is not nearly airtight enough to count as your field air sealing material. One way to think about this idea of continuity is the pen test. You take your finger or your cursor or a pencil, and without lifting it off the page, trace the control layer from the footing to the ridge in a building cross-section. It's going to be really tempting to jump at changes in assembly, changes in materials, changes in plane. More on this later. Yes, that air leakage can be sneaky. This home had a ceiling roof moisture problem even after the roof was re-insulated and air sealed. Using a blower door to pressurize the house along with a theatrical fogger, you can see the air leakage at the ridge around the ridge beam that extends from inside to outside the building, as well as at the V-groove deck boards, also moving from inside to outside the building. This just goes to show that if you don't do it right the first time, it can be really challenging to address later. Sometimes the air leakage moisture problem is obvious and unhidden, like in this picture of a finished attic. But it turns out that this is in a co-housing community, so there are about 30 very similar finished attics, some looking perfectly fine. Could the problem be hidden behind the drywall? To find out, I used long pins to penetrate all the way to the underside of the roof sheathing. I connected the pins to my moisture meter to measure the moisture content of the roof sheathing, leaving only 2 tiny holes to patch. Here is the moisture reading with the pins pushed all the way up to and slightly into the underside of the roof sheathing. Whoa, moisture content of nearly 40%. That is literally wet. So we tore down the drywall to find mold on the upper 1x3 strapping. When we took down the strapping and the cavity insulation, we found plenty of moisture staining near the top of the rafters and up to the ridge. We luckily caught all this before there was any structural damage to the roof framing or sheathing. The source of this hidden moisture? Air leakage at every ceiling penetration that wasn't sealed, mostly fire sprinkler heads and light fixtures. So sometimes the moisture problem can be seen, but more often than not, air leakage results in hidden moisture damage. Sometimes we're not so lucky. The air leakage and subsequent hidden condensation here has just started to rot out the top of the lower gambrel steep pitch and also the rafter for the top pitch just above that. This had to be repaired with structural plywood gussets to support the pitch change joint. This home was about 4 years old. Here is an unvented hip roof with air leakage trouble. The rotted roof sheathing required complete replacement. With the support of a structural engineer, we were able to repair the top half of the hip rafter and the ends of the rafters at the hip. This house was about 10 years old. The thing is, both these homes were built after 1990 and were considered tight homes. Even seemingly small air leaks can cause big trouble. So, where do we locate your continuous air control layer? You have three options, of course: continuous on the interior, in the framing cavity, or on the exterior. The most common approach on the interior is usually referred to as the airtight drywall approach, or ADA. You seal the margins of each drywall panel and margins of any penetrations or cutouts to each panel with a sealant or caulk. The sealant bead must be continuous to get a complete air seal. In the airtight drywall approach, or ADA, the continuous air seal material behind the drywall could be a gasket. But note that whenever you use the ADA, you might be counting on your drywall trade to get the air seal continuous. There will be some training and quality control required no matter who hangs your drywall with the ADA system. Next up is to get your air seal in your framing cavity, almost always with some sort of air impermeable spray foam insulation, acting as both your air seal and your insulation. We will be talking about spray foam later in this video and again in the insulation video, but in any case, if spray foam insulation is to be counted on for a continuous air control layer, care must be taken to individually air seal any place where air can leak that is not in the framing cavity, like between double top plates. Here is open cell spray foam as both cavity fill insulation and air control layer in a foundation wall. Here is closed cell spray foam in a roof assembly and closed cell spray foam in a wall cavity. Now note that the two closed cell spray foam applications do not fill the framing cavity. These cavities have been flashed with the spray foam as the air control layer, but the full complement of insulation will be completed with an air permeable cavity insulation. We will come back to this flash and fill or flash and bat approach in the next section on insulation. The final option for the location of the air control layer is the exterior. The air control layer can be the sheathing or a flexible sheet good like house wrap, or even liquid applied membrane, either applied to the exterior sheathing. One example of sheathing as the air control layer is the Huber zip system, where the tape completes the air control layer because the sheathing panel meets the air impermeable code standard. A major advantage of a continuous exterior air control layer is the lack of interfering assemblies, like floor systems and interior partitions. But wait, why a photo showing gypsum wallboard as part of an exterior air control layer? Well, if your attic is vented and your insulation is at the ceiling plane, then that is where the air control layer has to be, at the ceiling. So while the drywall is definitely inside the building in terms of bulk water management, the attic is technically outside of conditioned space or where the air control layer is. Now, the cool thing about how they drywalled this top floor ceiling is that they came and drywalled this ceiling separately and before any other drywall work was done, and before any top floor interior partitions were framed and installed. That means the air control layer at this ceiling is really continuous. No penetrations or cutting around interior framing. Sometimes better performance requires thinking outside the box a bit. While the field of any exterior wall is pretty easy to get airtight, there are a lot of tough spots. I'm reusing the zip system image because it reveals one of the top tough spots. where the exterior sheathing at the bottom of the above grade framed wall meets the top of the below grade foundation wall. One way to handle this transition area is to seal it with a proprietary sealant designed specifically as part of the wall sheathing system. This detail completes the continuity of the air control layer at the above grade wall to foundation wall transition. Now, it's really pretty simple. If you make a hole in an exterior wall or any part of the building envelope, you own it and you need to seal it. Make sure your scope of work for each trade that makes holes in your building envelope has clear responsibility for sealing every hole. There are manufactured gasket products that can be configured for pretty much any size penetration, and then there are air sealing materials that site seal penetrations. The building code, section R402.4, has a mandatory list of places to air seal, but wouldn't it be nice to have a checklist? In fact, we do. Some time ago, the EPA Energy Star program gathered a bunch of leading home energy auditors, and they spent considerable time and effort coming up with about 24 of the most common thermal bypasses, places in the home that tend to not get either air sealed or insulated. Now, if you use this checklist, you're well on your way to covering the list in the code, as well as meeting the air tightness code requirement. You can see that there are 6 categories in the checklist, with the first one being overall air barrier and thermal barrier alignment. More on this topic in the video on insulation. Note that some elements are dependent on climate, like under number 1, and for every item there are checkboxes for corrections needed and checkboxes for builder or rater verified. It's a list that has stood the test of time in our industry. But my good friend and architect Steve Basic, he just hates checklists. After all, he is an architect. So Steve took the checklist and turned it into a drawing. That's what architects do. If you work your way through this drawing, you will be well on your way to understanding comprehensive air tightness in your homes. In a way, Steve has translated the pen test into a 3D expression, at least for the most common jumps in a pretty typical home. I think one of the trickiest and most common thermal bypasses is exterior walls behind tubs. That's 2.1 on the checklist. But frankly, all of these can be challenging. My cut on the checklist versus the drawing, I think we need both. Now note that for windows, Steve just colored in the whole thing as a thermal bypass. There are 2 ways that windows can leak air. The first is the window unit itself. These 2 window labels are on pretty much all windows these days because almost all window manufacturers submit their window units for modeling analysis and testing by the National Fenestration Rating Council, the NFRC. We will talk through some of the other NFRC ratings, but for now, let's focus on the AL or air leakage number. For the left-hand sticker, the AL number is 0.2 cubic feet per minute per square foot of window area. Is that good or bad window air leakage? Well, the 2018 code requires that all windows be no more than 0.3 cubic feet per minute per square foot. So 0.2 seems pretty good, and it will certainly meet the code. But what about the NFRC window sticker on the right? In the box where the AL number should be, there's just a dash. It turns out that while the code requires you know and be able to prove the air leakage of your windows, this particular rating is optional for the NFRC window label. So where does that leave you as a builder or architect? You either need to use windows that report their AL number on the NFRC sticker, or your building inspector, per the code, has the right to make you prove the AL number for all your windows. Usually this means you need to contact your window rep or window manufacturer and go through the hassle of getting third-party certification of your window air leakage. What about the second way that windows leak air? So this is a cross-section detail at the windowsill. There are important water control layer aspects of this detail, but this is a great example of where we need to honor the high-performance intersection of the water and air control layers. First, note that this window and rough opening are detailed to drain the sill rough opening. There is a sloped sill and back dam so that any water that leaks into the window opening has a way out at the bottom. And in terms of bulk water management, since any water that leaks is likely by gravity to end up at the sill rough opening, the drained rough opening is arguably the most important part of the water control layer at this penetration. But second, How do we air seal at the sill without clogging up draining at the sill? We complete the window rough opening air seal at the sill by moving it back all the way to the back dam. This often means that sequentially, we are air sealing around the window rough opening completely after the window installation and flashing have been completed. There is an easy space for air sealing between the rough opening and the window unit at the head and jambs. But what about at the sill? The sill air sealing component can't run between the rough opening and the window at the sill. So the sill air sealing, most often a bead of sealant or foam, simply needs to connect at each end to the air seal at the jambs. By the way, a pressure-sensitive adhesive or PSA tape can be used here as well. More on choice of air sealing materials a bit later. The air seal at the sill is just as important as the air seal at the jambs and head. It's just that the sill air seal has to play nice with the sill bulk water drainage. Again, the intersection of air sealing and water management. It's always good to get solid resources from any training, so here is a go-to resource: Building Science Corporation's Enclosures That Work. In terms of field tested and practical, it doesn't get any better than this. So where is the air control layer in this enclosure? It's exterior, with the main components being the XPS or extruded polystyrene sheathing and the PSA tape at the XPS panel joints. Note how the 4x8 sheets of XPS are run vertically so that the full length of the sheet is supported at the framing joint. A key to this assembly is what PSA tape to use on the XPS sheathing. Material compatibility is a big part of air control layer continuity, so either use the tape recommended or required by the XPS manufacturer, or field test your choice of PSA tape to make sure it bonds well to the rigid insulation. And just a little side note here, yes, this assembly would definitely require the addition of structural sheathing interior to the XPS sheathing or some shear bracing system in place of the structural sheathing. Remember that while air control layers start with the right or required air tightness of individual materials, it's really when you put them all together in an air control layer system that you get performance. The Air Barrier Association of America uses the American Society of Materials, ASTM. It uses their standard E2357 for the wall assembly as shown in this image, with a set of standard penetrations. These standard penetrations capture many of the tough spots for air sealing. And you can see there's a duct, there's a pipe, there's a window penetration. These are all typical but standardized in this test. Every wall building assembly tested is set up exactly the same way. So this image shows the Georgia-Pacific Den's Defy wall system using GP's Den's element sheathing panel and their liquid applied membrane. It is set up for an ASTM E2357 air tightness test. Most of the approved and tested ABAA listed wall assemblies are more typical of commercial buildings, but there is quite a bit of crossover to home building. A major new part of the code related to air leakage is the requirement for a blower door test. So let's start this discussion with just what a blower door test is. You close all exterior doors and windows and open all interior doors, including the basement door, if there is one. And if, of course, the basement is conditioned space. That means inside the location of the air and thermal control layers. The blower door creates a pressure difference of 50 pascals, about the same as a wind blowing 20 miles per hour, but equally from every direction on the building. Now, just a note, while you can run the blower door turned around to pressurize the building, that can be more difficult because closures on bath and kitchen exhaust ducts are pulled tight when you depressurize the home, but not so if you pressurize. The code does not explicitly state which test to use, but just about everyone runs a depressurization blower door test. The blower door test is affected by wind, so if it's really blowing, particularly gusting, you might have to wait or reschedule, but the blower door system can accommodate some wind. The test itself takes only a few minutes, but setup can take at least a half an hour. The blower door system measure both the pressure difference of 50 pascals as well as the airflow through the blower door in cubic feet per minute. That number, the CFM 50 cubic feet per minute at 50 pascals, along with the house volume, allows calculation of the ACH 50. That's the number of air changes per hour at 50 pascals. That's the number required by the code. If you meet or exceed the required performance of 3 ACH 50, you're good to go. If you don't, you will need to go around inside of the building and identify areas of leakage to correct and improve your ACH 50. So this is a performance test. Now, I speak from personal experience. The first time I performed a blower door test in my own home, where I had done all the air sealing work myself, I was so angry because of all the places I missed. Now, granted, for me, it was an existing older home and leaks were everywhere, but the point is, be prepared your first time around to be disappointed and need to go around your building and learn. How hard is it to get to 3 ACH 50 or lower per the code? Well, the average new home in the US is about 5 to 7 ACH 50, so it requires diligence, but not craziness. It won't take you long to use this training and figure out how to consistently deliver 3 ACH 50 or lower. The building code does not explicitly state just what blower door systems are acceptable or not, but the code references standards that require certain levels of accuracy for the blower door fan and pressure gauge, and that this equipment be calibrated per the manufacturer requirements. Now that said, there are 2 primary blower door kit manufacturers. Here you see me with my Retrotec blower door kit. The shroud is fit to the door by the cammed door frame. The fan sits in the shroud and door frame, and the fan is connected by tubing to the digital pressure gauge. Here is my Minneapolis blower door kit from the Energy Conservatory, showing the pressure gauge mounted to the edge of the door. Both blower door kits are code-worthy. The blower door test is really pretty simple, but the equipment is quite sophisticated. Both the blower door fan and pressure gauge need to be handled with care, but they are field equipment, so they're robust and long-lasting if treated like any other expensive tool on your job site. You can read the blower door gauge. It says minus 50.1 pascals of pressure, and the flow through the fan is 1,362 cubic feet per minute. When I measured the home's volume and calculated the ACH 50, I got 1.2. This was a new home, timber framed, with a panel package that wrapped the entire timber frame. 1.2 ACH 50 is well below the required 3 ACH 50. This is a pretty tight home. Note, though, that really airtight homes can be as low as 0.6 ACH 50. That happens to be the required air tightness for the Passive House program. That is 5 times tighter than required by the code. So as I said, 3 ACH 50 requires attention to detail, but if you follow the Energy Star thermal bypass checklist, you are well on your way to code compliance for air leakage. Sometimes pictures are worth 1,000 words. I have found that to be the case with air leakage in buildings. It can be hard to convince either building owners or trade contractors that air leakage, completely invisible, is a big deal. So this infrared image was taken during the winter from the inside of the home, looking up at the timber frame ridge in the living room. Bright yellow represents the warmest color at a surface temperature of about 73 degrees Fahrenheit, and the coldest surface temperature at the edge of the windows, that's purple, is about 51 degrees Fahrenheit. Looks as though the timber frame roof is doing okay in terms of thermal bypasses like air leakage and thermal bridges. But this next image was taken in the same home after I turned on the blower door and depressurized the home, pulling in cold outside air. All that streaking is air leakage that was completely hidden because without the blower door running, warm air was leaking out and the surfaces at the ridge were warmed by that leaking air. And without ladders or staging, you would not be able to feel that cold air leaking in with the blower door running, but adding the IR camera makes it easy to find those air leaks anywhere in the home. Now, you don't need an infrared camera to figure out building performance, but it sure helps. There are big portions of the year, regardless of climate, where IR imaging is challenging because the temperature difference inside to out is not great enough to reveal air leakage locations and patterns with an infrared camera. So we flip the blower door around and pressurize the house while running a theatrical fogger inside. Yeah, there is more prep for this approach, but plenty to learn about air leakage this way. Now, a note of caution. Disconnect or seal off all smoke detectors and make sure that either all of the neighbors or the local fire department know what you're up to. Theatrical fog's resemblance to smoke is simply a bit too close. Just a quick couple of points about the sticky stuff we use to connect components of our air control layers. I wrote a 15-part blog series called Sticky Business. So for more detailed information on building industry sticky stuff, go to buildinggreen.com and search under the topic Sticky Business. But some key takeaways from that work. There are two types of joints that liquid sealants can address. This first image is a planar joint with the sealant taking the shape of an hourglass and with backer rod in the joint below the sealant. The second image is a corner joint. The sealant bead goes into the corner after a bond break tape is installed in the corner as well. So in both configurations, note how critical the joint and sealant performance is to the proper bond break at the back of the sealant. I don't think I ever used a bond break, such as backer rod or the backer tape, when I was a full-time builder remodeler. The other key mistake I regularly made about liquid sealants was simply buying the cheapest latex acrylic at the hardware store. There are a lot of different types of sealants, each with strengths for different applications, including material compatibility with the substrate. So we got to get the sticky stuff right. More sticky business. All the construction adhesive tapes I know of are pressure sensitive or PSA tapes. They all only stick well if we use pressure. The pressure liquefies or wets the adhesive so it penetrates into the surface of the substrate. Without the pressure, the bond is much weaker and shorter lived. In my work with both liquid sealants and PSA tapes, I trust the tapes to handle contraction and expansion areas more reliably than sealants. It's just a personal preference. But again, for more detailed information about all ways to make connections with sticky stuff, go to the article I wrote on buildinggreen.com called Sticky Business, and you're on your way. There are two special air sealing materials I wanted to discuss, the first being spray foam. The most important thing to point out about spray foam is that both open cell and closed cell spray foam qualify as air impermeable according to the code definition. So while there are significant differences between these two from an insulation perspective, they both can be a key component of your air control layer. The thing that is special about spray foam is that it is almost certainly the only building product that is entirely manufactured on site. And the chemistry is both elegant and complex. There are a lot of things that need to go right and quite a bit for the trained technician to master to get spray foam installation right. I recommend going with third-party certified companies, even knowing that these companies' installers will almost certainly never be the lowest bid. This spray foam truck looks more like a lab than a trade contractor vehicle. In fact, best practice spray foam rigs should be more like a lab. The second special air sealing system is the aero barrier system. Now, to be clear here, I am not recommending products here, but this is a unique and innovative approach to air sealing that you should be aware of. So here's how it works. Misting heads are located throughout the building, and the building is pressurized to 100 pascals, positive pressure with a blower door. The misting heads put very tiny droplets of a proprietary adhesive into the air. The particles are so tiny that they are suspended in the air. The positive pressure of the blower door means that these tiny particles get stuck as they move through all the air leak locations, building up until they seal off the leaks. This process can take a couple of hours, depending on just how airtight the building is to begin with, and just how airtight you want the home to be. You can basically dial in your desired airtightness with this system. Now, this system is very sophisticated, requiring proprietary equipment and materials and extensive training for the aero barrier installers. But the appeal of this system to meet the building code required 3 ACH or less is pretty obvious. This last image is from a test panel where I and another building scientist are trying to assess the long-term durability of the aero barrier seal when through materials like PVC and copper pipe expand and contract over the course of seasons or even years. If we are going to rely on sticky stuff to seal our buildings, we need to be confident that they will last. So just a bit of an air sealing wrap up. Leaking air is double trouble. You pay for that conditioned air leaking out of your homes, or your customers do, and hidden moisture problems represent risk and potential liability. To get a continuous air control layer, start with the right materials and then connect them. The 2018 code makes air sealing mandatory, including performance testing. We depend quite a bit on sticky stuffs to seal our buildings. Make sure that you use each one in the way it is intended. There are lots of ways to get an airtight home. The new code allows you to decide how to get there. We hope we've shown you some real-world examples of the new code's focus on and the importance of moisture management, air sealing, and insulation. Join us for a deeper look at insulation and the 2018 code as we continue this series. Thanks for watching.